Um, okay. Questions before we begin? On anything, let's start with anything not pertaining to Chapter 11. Cool. I think we have a homework assignment due today, correct? This is 5?
I think so.
Okay. Cool. All right. Chapter 11. Any questions? I guess I can probably stop asking that question at the beginning of class because I know that nobody reads the chapters. You read the book? You started reading the book now. Good. Okay. So, Chapter 11 talks about searching, and that's kind of an inaccurate title for this chapter because it's kind of a bunch of different concepts. We have searching, we have hashing, we have using Java's hash table class, and some more hashing. So, most of this chapter is hashing, and very little of this chapter is on searching. The searching we can go through in about 5 minutes. There are 2 searching methodologies described by the book. There's something that the author calls serial search. I've seen it called linear search. I've usually seen it called linear search. This approach is basically the simplest possible, stupidest approach to looking through a list of things. It's the approach we used for the contains method when we built a linked list. Basically start at the beginning and look through the list until you find the element you're looking for. If you get to the end, you haven't found it, it does not exist in the list. And it's called linear search or serial search because it starts at the beginning and looks at each element in turn. Benefits of linear search or serial search are that you don't have to make any assumptions about the nature of the data in the list or array or other data structure. Because you're looking at each item until you either find the item or you get to the end of the list. So it's also called an exhaustive search because it looks through every element potentially. If it doesn't find the element, it looks through every element. If it does find the element, it can short circuit. So it has a best case runtime of 1. If the element you're looking for is at the beginning, whatever beginning means, the first place you look of your data set, then you can look at the first element, see that it's the element you're looking for, and you're done. It doesn't matter how big your list is, it always takes 1 operation. The worst case is n. If you have n things in your data set, the worst case that could possibly happen is the element that you're looking for is all the way at the end. You have to look through every single element and not find it, and then you get to the last element, you find it, and you're done. This is kind of what we do when we lose something in our houses, and we go looking for it. And surprisingly, it's always in the last place we look. The reason being that once we find it, we don't have to look anymore. So an added benefit is that it does short circuit. So on average, on completely random data, the average runtime is n over 2, which with runtime complexity ends up just being n, because it's a constant multiplied by n, the n takes over. Because some of the time it'll be further than the middle element, some of the time it'll be before the middle element, and those 2 cases will kind of balance out, and most of the time, if you ran a linear search lots and lots of times, you would end up with a runtime proportional to, an average runtime proportional to half the size of the list. Right. However, if our list is sorted, we can do better than that. And I think I've probably already mentioned this. When we talked about binary search trees, I get the feeling that I talked about this. Binary search takes advantage of the knowledge that a list is sorted. Picks an element in the middle and determines, is the element I'm looking for greater than or less than this middle element? If it's less than this element, it looks in the left half of the list. If it's greater than this element, it looks in the right half of the list. And performs the same thing on this smaller array. So on page 580, Java contains a binary search method. And that is why this binary search method takes an array, a starting index in the array, an ending index in the array, and the thing it's looking for. Which screams that this method actually calls itself somewhere in there. So it basically says, I'll start with this big array and pick the element in the middle, compare that to target, and then call the same method on the smaller chunk of the array that the target will be in. The part of the array that is not the part of the array the target will definitely not be in. Because we might not find target. Target might not be there. And there are a couple ending conditions in this recursion. One ending condition is that the array that I'm looking at doesn't have any elements in it, in which case I'm done. Another ending condition is that the element that I chose to look at to determine which subarray I'm going to continue looking at is actually the element I'm looking for, in which case I've found it and I'm done. I think those are the only two ending cases. So it's basically, it has a very tree-like feeling to it. And you can actually, that's basically how binary search trees operate. They take this one-dimensional array and turn it into a two-dimensional structure. So they operate exactly the same way. One is just more visual than the other. So that's searching. That's all that the book talks about in terms of searching. The rest of the chapter talks about hashing. So, Dion, you read the chapter. What is hashing? You said you read this chapter. Oh. Did you read this chapter? Okay, that was section 11.1. Did anyone read section 11.2? You got an older version of the book? Okay. That's the section on hashing. Don't know. Okay. So the basic idea behind hashing is if we can, so arrays are constant time index. So with a tree, a linked list, anything like that, we have to go through some effort to get at a specific element within the data structure. Arrays, we want the element at index 4. We say array square brackets 4, and we get the element at index 4. That's it. One operation, we're done. But there are a lot of downsides to arrays, which all of the other data structures try to make up for. However, it would be really nice if we could still maintain that constant time indexing. So one way that we can accomplish that, basically the only way to accomplish that is to figure out some unique index that we can choose for every key or value, depending on whether we're using the book describes it as a table-like data structure or the standard value collection data structure that we've been using. So given a particular value, we can say, if it is in this table, if it is in this data structure, this is exactly where it will be. Or with the table data structure, given this key, this is exactly where its respective value is going to be. And that's, long story short, that's called hashing. Basically taking the data that we use to find a particular value, either the value itself or the key, depending on what type of interface we're dealing with, and determining a specific location. So a specific array index, for instance. And usually, since Java's only built-in data structure, I'm taking some liberties with the terms there. Since Java's only built-in data structure is an array, it makes sense to take whatever we're using to key this data and turn it into an array index. And that function, in the mathematical term, is the hashing function. So even if we're dealing with strings, we take the string and somehow turn it into an int. If we're dealing with ints, we somehow take that and turn it into an int, which really shouldn't be all that hard. If we're dealing with doubles, we take that and somehow turn it into an int. And the idea is that we have enough slots in our underlying storage mechanism to store any possible data that we want to store in this. But depending on how much data we're storing, that's not always the case. So we end up with something called collisions. And there are a few different ways that we can deal with collisions, which we'll get to in a minute. But with using this hashing function, we have an extra layer of abstraction. So this allows us to have an array as the underlying data storage mechanism and have some other type of interface on top of it. So with the table, we can specify a key of whatever type we want and use that, hash that, and determine where in the array its corresponding value is stored. Which also means that since we're now creating a data structure around this array, we can also treat it as a tree, a linked list. Well, it would be kind of weird to treat it as a linked list, but a tree, a queue, whatever. So we have the benefits of being able to efficiently search this data structure that we get from something like a tree, and we get the advantages of direct indexing that we have from an array. So it's kind of the best of both worlds. Useful in specific cases. So collisions. How do we deal with collisions? So the one way and the best way, but also the most ideal and most likely to be impossible way, is to choose a hashing function that doesn't lend itself to collisions. So everyone's heard about MD5. The idea behind MD5, as it's used now, it used to be used for passwords, then it got cracked. So it's not used for passwords anymore, or it shouldn't be. Now it's used primarily for checking to make sure that files haven't changed in transit, for instance. The idea being that MD5 is a very unique hashing function. For any two input files, there is a very, very low likelihood that they will result in the same MD5 hash. So even if you take one file and change a few bits in it, you should get a completely different MD5 hash out. Of course, so another one of the reasons that hashes exist is it's a lot easier to talk about MD5 hashes are 16 characters, I think. A lot easier to talk about a 16-character string than a massive file. It's a lot easier to say this MD5 hash is not the same as this MD5 hash. These files are not the same, as opposed to, is this file bit for bit identical to this other file? And die on the first bit. Because if that last bit is changed, if the only difference between these two files is that last bit, you have to go through every single bit of the file until that last byte, see that those two bytes are not the same, and then determine that the files are different. With an MD5 hash, you only have 16 characters, and those MD5 hashes are going to be wildly different just because of that one bit change. So you can very easily tell that these two files are not the same. How do I get started talking about MD5s? Right, uniqueness. So MD5 is a very good hash. You need, both because of its size, it's 16 characters, those are all hexadecimal numbers, so each character has 16 possibilities, so that's 16 to the 16th. Lots of possible MD5 hashes. So you would need a lot of files before you started having to worry about collisions. Usually it's about half the number of hashes, I think. I'm a little fuzzy on my hash memory. So, right, MD5 is very unique. Not all hashes are as unique as MD5. Sometimes they don't have to be. Sometimes you can also construct hashing functions so that data that is similar in some way results in the same hash. So there are only certain things that, if they're different, they should get wildly different hashes. And it really depends on the use case. But if you don't have a very unique hashing function, you're going to run into collisions. And eventually, with something like MD5, you'll run into collisions too. So the question is, what do you do when you can't avoid collisions? And there we go, 11.4. Most of the sections of this chapter are like a page long. With the chain hashing, take a step back. One way to deal with collisions is to do something called chain hashing. So in a chain hashing situation, it is okay if multiple things result in the same hash. Because basically every slot in whatever your underlying data store is actually a linked list. So in this case, the hash is not intended to uniquely identify the particular piece of data, but significantly reduce the number of pieces of data that you have to look through in order to find it. So each individual element in, say, your underlying array is a linked list. So whenever you're looking for a particular element, you compute the hash of it, figure out which array element it should be in, then look through the linked list, which is maybe only 2 or 3 items for the actual item you're looking for. So it speeds it up. It speeds things up significantly without using up a whole lot of memory. And Java actually has a couple data structures built in that use hashing. The book talks about one called hash table. There's another one called hash map. So I'm going to try something and we're going to see if it actually works. So the book talks about hash table, which we can look for here, hash table. And this says, this class implements a hash table, which maps keys to values. Okay. Implements map. Let's see if we can find a map that doesn't use a hashing function. Known implementing classes. Abstract map, that's not going to work. Hash map, hash table. Tree map. So, tree map, the way Java classes are named is underlying data structure and then interface, and they're smashed together. Both pieces have capital letters. So, tree map implements the map interface with an underlying with a tree as its underlying data storage mechanism. Hash map, on the other hand, implements a map with this hashing thing as its underlying data store. And the difference between hash table and hash map, that is a good question. One implements a dictionary and one implements an abstract map. What is a dictionary? Wow. Very similar. I expect that the difference is a dictionary is probably ordered, whereas a map is not. Let's see what this is. Every key is associated with at most one value. Whereas a map, what does map say? Oh, this interface takes the place of the dictionary class, which was a totally abstract class rather than an interface. So there's absolutely no difference between them. So even though the book uses hash table, I'll use hash map just so that we're using hash map and tree map. They both have map in them. Any objections? Cool. So public class map battle.
So let's create a. So do I need anything special in order to use either of these? Java.util. Import java.util hash map. I'm going to assume they're both in the same package, and hopefully my assumption will be right. Let's do a string to an integer. No, let's do a string to a string. Hash map. Let's do hash map. String. I believe hash map means that it has a put abstract map. Put and get. So put oh geez, I want to do characters to actors and actresses, or vice versa. Which means I have to pick a movie that I know a lot of them for. Let's go with this. Not a movie, but oh geez, I have to remember how to spell this name. I think that's right. Is 5 enough? 7. 7 should be good. You've all by now figured out what TV show I'm going with, correct? You should have guessed based on the first one. This would be 24. Tree map. And now for the exciting part. I think that's the name of it. Current time millis. There we go. And inside here, I am going to string. Let's put as little as possible between those things. So this is hash map get. And inside the other one, we will put free map. And hopefully this will be there. This will take long enough that there will be a difference. We'll find out in a minute. Okay,
Does everyone follow what I'm doing? Now, the assumption is that, based on what we've just said about hashing, that hash map should be quicker. Hash map should be almost linear time, whereas tree map should be log base 2 of the number of elements.
So, file, and watch it blow up. Not find symbol. Class string. Oh yes, that is accurate. There we go. Okay. It runs a little too quick. Is there anything that can get us here we go. Nano time. Let's do that. Whoa. Okay.
Hash map is quite a bit quicker than tree map.
And that makes sense, right? Unfortunately, I think I'm out of 24 characters that I know. So what we're going to do is take these 3, put them down here, take the same 3 from tree map, put them down here, and we'll do the same thing as far as testing. So the expectation is that with hash map, the time to find out who plays Aaron Pierce should take the same no matter how many elements are there, how many actors are in the hash map. But with tree map, it will get slightly longer, though we might not have added enough characters to make a significant difference. That is slightly odd. What we're seeing is that there's actually not enough going on here to make a significant impact. So sometimes it'll take longer to run this function, and sometimes it will take less time. So we can actually run it a few times. And ideally, we'd kind of compute the average of all of these and see what happened. But But you can see that, in general, the tree map numbers are greater than the hash map numbers. And in general, the second tree map number is larger than the first tree map number. Let's add a bunch more people. Try to get those numbers to be more different. I put it on the screen down here so I could type and look at it at the same time. He also plays Spock in the most recent Star Trek movie. Okay, that should help us out on the times. It shouldn't matter that we're looking for the same thing over and over again. But it should obviously take longer to get multiple entries. These numbers aren't making any sense at all. So, yeah. I am actually setting start and end, right? Yes. Well, so my my demonstration didn't really demonstrate what it was supposed to demonstrate, but hash map is more constant time than a tree map. Because a tree map is essentially what you're implementing for today. So it has to go down all the levels of the tree, which brings up a good question. I don't actually know if this tree map is a binary tree. It could be a B tree. It just says tree. It doesn't specify what kind of tree. If it were a B tree, then yes, it could get probably almost as quick as hash map. So that could be what we're looking at. So questions on hashing versus other methods of locating data? Oh, red-black tree. Red-black trees are very quick. We didn't talk about red-black trees. So, questions? No? The book doesn't even talk about red-black trees. If you're interested in red-black trees, you're welcome to read about them on your own. I'm sure Wikipedia has an excellent article on it. Red-black tree. Self-balancing binary search tree. Okay, that's pretty much all of that chapter. On Monday we'll talk about sorting, and I'll stop the video, then we'll do FCQs, and after we do FCQs, you're welcome to work on the programming assignment that's due today. I'll be here to answer questions, but there's nothing more formal for this class.